Chemistry Standard 12 Solid State Part 2. Calculation of number of particles in unit cell. A crystal lattice is made up of very large number of unit cells. Each unit cell is touching a number of unit cells. In unit cell, every lattice point is occupied by one constituent particle. Thus, a constituent particle present at a lattice point may be shared by a number of unit cells. Let us now understand the contribution of particles in lattice point to its unit cell. A corner atom is shared equally by 8 unit cells. 4 unit cells are present at the lower layer and the 4 unit cells are present on the upper layer. Therefore, each corner atom contributes only 1/8 atom to a particular unit cell. Face-centered atom. A face-centered atom is shared equally by 2 unit cells having a corner face. Therefore, an atom present at the center of the face of the unit cell contributes half atom to each unit cell. A body-centered atom is not shared by any adjacent unit cell in crystal lattice. Therefore, it contributes fully to unit cell. Edge-centered atom is shared by 4 adjacent unit cells in a crystal lattice. 2 unit cells are present in the lower layer and 2 unit cells are present on the upper layer. Therefore, it contributes only 1/4 of its cell to a unit cell. Calculation of number of atoms per unit cell in primitive cubic unit cell. In simple cubic unit cell, there are 8 corners in the cube. There is one atom at each corner of the cube. Since each corner atom is shared equally by 8 unit cells, hence each corner atom contributes 1/8 atom to each unit cell. Number of atoms in one unit cell. Simple cubic unit cell equal to 8 multiplied by 1/8 equal to 1 atom. A simple cubic unit cell contains 1 atom. A simple cubic unit cell contains 1 atom. Calculation of number of atoms per unit cell in body-centered cubic unit cell. In body-centered unit cell, there are 8 corners at each corner position and 1 atom at its body center. As each atom at the corner position contribute 1/8 to the unit cell, the contribution of those 8 corner atoms to the unit cell is 1 atom. The atom at the center of the unit cell is not shared by any other unit cell, thus its contribution to its unit cell is whole, and hence the number of atom body center, that is 1 plus 1 equal to 2. 8 corner atoms. 8 corner atom multiplied by 1/8 equal to 1 atom. 1 body centered atom equal to 1 into 1 equal to 1 atom. Therefore, number of atoms per unit cell equal to 2 atoms. Thus, a body-centered cubic unit cell contains 2 atoms of an element. Calculation of number of atoms per unit cell in face-centered cubic unit cell. In face-centered cubic unit cell, there are 8 atoms at the corner position and 1 atom at the center of every face of the cube. As each atom at the corner position contributes 1/8 of the unit cell, the contribution of these 8 corner atoms to the unit cell is 1 atom. Each atom at the face centered is shared between the 2 adjacent unit cells. Thus, the contribution of 6 such faces center atom to the unit cell is 6 multiply 1 by 2 equal to 3 atom. Therefore, the total number of atoms per face centered unit cell is 1 plus 3, that is equal to 4. 8 corner atoms multiply by 1 by 8 equal to 1 atom. 6 face center atom multiply by half atom per cell, that is equal to 6 multiply by 1 by 2 equal to 3 atom. Therefore, total number of atoms per unit cell equal to 4 atoms. The face-centered cubic unit cell contain 4 atoms of an element. The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps: packing in 1 dimension, 2 dimension and 3 dimension. Close packing of a sphere in 1 dimension. In 1 dimension close packing, there is just one way of arranging the sphere. Here the spheres are arranged in the row touching one another. As a result, each sphere is contact with 2 other neighboring spheres. Thus, in 1-dimensional close packing, coordination number is 2. Close packing of a sphere in 2 dimension. Close packing structure in 2 dimension can be generated by stacking rows of 1-dimensionally close packed sphere one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of sphere is placed in contact with first row in such a way that the sphere of the second row are placed exactly above the sphere of the first row. In such arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So the coordination number is 4. If we call the first row as A type row, the second row is being exactly same as the first row, so it is also called A type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AA type of arrangement or square packing. Hexagonal close packing. In this type of packing of a sphere, second row sphere is placed in a staggered manner such that the sphere fit in the depression of the first row. If we call the first row as A type, then as the second row is different from the first row, it can be called as a B type. Now if we placed third row above the second row in similar manner, we will observe that the third row sphere are aligned with those of first layer. Each sphere is in contact with 6 other spheres. So coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of sphere are aligned with those of second layer. So this type of arrangement is known as AB-AB type of arrangement or hexagonal close packing arrangement. If we compare square close packing with a hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty space in between the sphere is called void. These voids are responsible to decrease the packing efficiency of the solid crystal. More the number of void, less is the packing efficiency of the crystal. Now you must be wondering, what is the meaning of packing efficiency? We have discussed about this in the latter part of the section. Now let us study about close packing in the three-dimensional close packing from two-dimensional square close packed layer. This type of packing attained by placing two-dimensional square close packed layer above the first one such that the sphere of the second layer is just above the first layer. In this arrangement, the sphere of both the layers are perfectly aligned horizontally and vertically. On arranging the layer one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere, so the coordination number is 6. If we call the first layer as A type, and since all the layers are also same type, this kind of arrangement is known as AA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cube lattice, and its unit cell is primitive cubic unit cell. Three-dimensional close packing from two-dimensional hexagonal close packed layer. The three-dimensional hexagonal close packed structure can be obtained by placing two-dimensional hexagonal structure one layer above the other. Placing second layer over the first layer. Let us take two-dimensional hexagonal placed layer A. Notice this layer has triangular void. Placed similar closed packed layer in such a way that the sphere of the second layer are placed on the depression of the first layer. As the sphere of the second layer are aligned differently as compared to the first layer, so let us call this layer as a B type of layer. On observing, we will notice that not all the triangular voids of that first layer are covered by the sphere of the second layer. This gives size of different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids denoted by T and octahedral voids denoted by O. Let us study how these voids are formed. When we placed a close packed layer above the depression of the first layer, we will notice that at same places the triangular voids of the first layer are being covered by the sphere of second layer. At such places a type of void is formed, and this type of void is known as tetrahedral void T. Since a tetrahedron is formed by joining the center of 4 surrounding spheres, while at the other places we will notice that the triangular voids of the first layer coincides with the triangular voids of a second layer, such that their triangular shape do not overlap. At such place, another type of void is formed, and this type of void is known as octahedral void. Since a octahedron is formed by joining the center of six surrounding sphere. Now in case we need to calculate the number of tetrahedral and octahedral void in a crystal structure, then just knowing the number of sphere will serve the purpose. Suppose there are n number spheres in the crystal, then the number of octahedral void generated is equal to n, and the number of tetrahedral void generated will be 2n. Placing the third layer over second layer, now let us place third layer over the second layer. Arranging third layer over the second layer can be done by two ways. First, by covering the tetrahedral void. Second, by covering the octahedral voids. By covering the tetrahedral voids. Tetrahedral voids of the second layer can be covered by placing the sphere of the third layer over them. On doing so, the sphere of the third layer will get exactly aligned with the sphere of the first layer. So, if we can call the first layer A type and the second layer as a B type, then the third layer will also be A type. As the pattern of a sphere is repeated alternately another layer, so this pattern is known as AB-AB type of pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. By covering the octahedral voids. The octahedral void of the second layer can be covered by placing the sphere of the third layer over them. On doing so, the sphere of the third layer are not aligned with the sphere of either first layer or second layer. So, if we call the first layer as a A type, the second layer as a B type, then this third layer will be C type. Now we will be placed fourth layer over the octahedral void of the third layer. Then the sphere get aligned with the sphere of the first layer. Thus this pattern is known as ABC-ABC type, and the structure formed is known as cubic close packed structure CCP, or face centered cubic FCC structure. In this type of structure, each sphere is contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Packing efficiency in crystals. The particles such as atoms or ions or molecules in crystal can be packed together in several different ways. In each type of packing, there is always some vacant space in between the constituent particle in the form of voids. We know that there are two types of voids in packing: tetrahedral void and octahedral void. Thus, in a packing, only a part of total available space is occupied by constituent particles. The percentage of total space filled by the particle is called packing efficiency. Different type of packing arrangement have a different packing efficiency. Now let us calculate the packing efficiency in different packing arrangements. Packing efficiency of simple cubic lattice. In simple cubic unit cell, the 8 atoms or particles occupied the corner position. Therefore, the particles are in contact with one another along the edges. The number of atoms per unit cell in simple cubic is only 1. Each atom is considered as one sphere. Volume of the one atom or one sphere is equal to 4 by 3 pi r cube. Let A is the edge length of the unit cell and r is the radius of the sphere. The spheres in the corner are touching each other. Then we have edge length A equal to 2r. The volume of a cubic unit cell, that is equal to A cube. In the place of A we will keep 2r, so 2r cube, and that is equal to 8r cube. Percentage of the space occupied by a sphere or packing efficiency equal to volume of one atom divided by volume of cubic unit cell multiplied by 100. Here in this formula we can see that we have taken volume of one atom, which is for a simple cubic. When we calculate the atom, we will get total number of atom in simple cubic is 1. So we have taken volume of one atom, that is divided by volume of cubic unit cell multiplied by 100. Now in this formula, volume of one atom, that is value is 4 by 3 pi r cube we will keep, and in the volume of cubic unit cell we will keep the 8r cube. So packing efficiency equal to 4 by 3 pi r cube divided by 8r cube multiplied by 100. We will get pi by 6 multiplied by 100, that is equal to 52.36%, and that is equal to 52.4%. The vacant space available in simple cube, that is equal to 100 minus 52.4, that is equal to 47.6%. It means in simple cube lattice only 52.4% part is covered by the unit cell. Rest 47.6% is in empty space. Packing efficiency in HCP and CCP structure. Face-centered unit cell. Let us calculate the packing efficiency in CCP structure. Cubic close packing is same as face-centered cubic packing. In this type of arrangement, the particles are touching one another along the face diagonally. Let the edge length of a unit cell is A. The radius of each sphere is R. The face diagonal is B. AC equal to B equal to 4R. We can understand this by keeping here. You can see only A to this half part will be R radius. Then in the next one, this circle, you will have another half. Then downward another third half, and the rest one, that will be R. A to C will be total 4R will be there. why we have taken AC equal to 4R. Now let us calculate the edge length A by applying the Pythagoras theorem. In triangle ABC, AC square equal to BC square plus AB square. BC square equal to A square plus A square. Here you can understand the AC is equal to B. So we have keep the value B. BC is also equal to A and AB is also equal to A. So here we have keep the value of that. So we will get B square equal to A square plus A square. So you will have B square equal to 2A square. Therefore, you will have B equal to under root 2A, that is equal to 4R. So A equal to 4R upon square root 2, which is equal to 2 square root 2R. Volume of the cubic unit cell, that is A square, which is equal to 2 square root 2R whole cube. We know that each unit cell in a face-centered unit cell or CCP structure have a 4-sphere or atom. Volume of 4-sphere equal to 4 multiplied by 4 by 3 pi r cube, that is equal to 16 by 3 pi r cube. Now let us calculate the packing efficiency. Packing efficiency equal to volume occupied by 4-sphere in the unit cell divided by total volume of the unit cell multiplied by 100%. Packing efficiency equal to 16 by 3 pi r cube divided by total 2 square root 2r raised to the whole cube multiplied by 100%. So that will, by solving this, we will get 16 by 3 pi r cube upon 16 under root 2r cube 100, and that is equal to 74%. HCP or CCP has a packing efficiency of 74%. It means 74 part is covered by the unit cell and rest 100 minus 74 part is the vacant space or a void. Packing efficiency in body-centered cubic structure. In body-centered cubic structure, there is a particle at the center of the unit cell in addition to the particle at the corner. Thus, in body-centered cubic structure, there is 3 spheres in contact with each other along their body diagonal. Let A is the edge length of the cube and R is the radius of the sphere. Body diagonal AF equal to C and face diagonal FD equal to B. Then AF equal to C, that is equal to 4R. Now let us calculate the body diagonal C and face diagonal B. Using this value, we can calculate A. Let us consider triangle EFD. By using Pythagoras theorem, we have FD square equal to EF square plus EB square, that is equal to B square equal to A square plus A square. So B square equal to 2A square. Therefore B equal to square root of 2A. In the triangle AFD, AF square equal to AD diagonal, which is equal to 4r. So we can write C equal to under root 3a, which is equal to 4r. So A equal to 4r by under root 3. Volume of unit cell, that is equal to A cube. So in the place of A, we will keep the value 4r upon under root 3 whole cube. In body-centered cubic unit cell, the number of particles per unit cell is 2 atoms. So each atom is considered as a one sphere. The volume of 2 atoms equal to 2 multiplied by 4 by 3 pi r cube, which is equal to 8 by 3 pi r cube. Now we can find out the packing efficiency. So packing efficiency is equal to volume occupied by 2 spheres in the unit cell multiply 100 divide by total volume of the unit cell. We'll keep the value 8 by 3 pi r cube divide by 64 3 under root 3 r cube multiply by 100. By solving this, we will get the value 68%. So packing efficiency is equal to 68%. In body-centered